Okay, so in question 21, looks like we've got a hydrostatic fluid question. So we've got a U-shaped container containing a mixture of gasoline and water. So sorry with the printing here, anything confusing. So this is, there's a piston here, top of the gasoline, this is gasoline. This is the cutoff at the bottom of the gasoline and the top of the water. There's also a piston here on top of the water, and the rest then is water. Okay, so we're told the container has a diameter of 4 centimeters, and the piston above the water has a mass of 5 kg, so maybe this is mass of the water, and this is MP. That's what we're trying to find, the mass of the piston above the gasoline, or use G, sorry. Yeah, for gasoline. Okay, so we're trying to find the mass of the piston above the gasoline. So how is that linked to, hydrostatic fluids and pressures? So this is somewhat linked to the tutorial. If we think about the forces that are exerted on the piston. So I'll draw an extended free body diagram for the piston. So there's a downward force by the atmosphere. The piston has a weight force due to its mass, and there is a normal force upward by the fluid. If the piston is at rest, we can state that the normal force by the fluid is equal to the normal force by the atmosphere plus the weight. Now, forces by fluids are linked to their pressures. The pressure is equal to force over area, so pressure times area equals the force. So I can describe the fluid force as the pressure of the fluid times the cross-sectional area of the container. Normally the atmosphere is the same, PATM times A, and this is M times G, mass of the piston times G, divided across by A, each term by A, and I'm left with the pressure of the fluid equals P atmosphere plus M piston G over A. And that's the equation you have seen in the tutorial. Okay, so I'll zoom back out here, and now we've got to connect all of this to our rules for hydrostatics. So some things that we can equate here for the container, so let me try to sort of maybe step back a second and think about how would you get there. So this comes from the forces. You're trying to solve for the mass of the piston. You don't know that. You can solve for A. You know P atmosphere, but you don't know the fluid pressure. So how do we determine the fluid pressure? Now we do know we could figure out the fluid pressure at just below the water piston, because we do know the mass of the water piston. So if I label this point here as point A, I could figure out the pressure of point A, because again, I know the mass of the water piston G, I know the cross-sectional area. Okay, I'm trying to mix up these two A's. Maybe I'll change my ordering here. I'll label this as I'm trying to think of some letters to use here that won't be confusing. I'll use the letter K. Okay. So I could figure out the pressure at K using the mass of the water piston, G, divided by the cross-sectional area, and atmospheric pressure. So how is that helpful? So because the pressure at this point is K, does not mean that the pressure below the gasoline pressure is the same, even though they're at the same height in the same container. They're not in the same fluid. But if I were to come down here and label a point L, I can also find the pressure at L, because I know that the height difference between K K and L. So we're told this is 15 centimeters. We're told that the diameter is 4 centimeters. So I know the height difference between K and L. Now the point L also has the same pressure as point M over here, because they're at the same height, in the same container, in the same fluid. And then that allows me to cycle up here to a point N where I want to know the pressure. So sort of I work through this process, then I have this unknown quantity P of N, and that will be linked to the mass of the piston above the gasoline. And that's sort of the process we're going to sort of work through. Again, not trivial. Okay. So what I'm going to start with is stating that the pressure at L equals the pressure at M. So same height, same fluid, same container. Now the pressure at L I can state is equal to the pressure at K plus rho water G times this value of H. Rho times H times G. I don't mind if you use H or G. And then the pressure at M is equal to the pressure at L, which is, pressure at N, plus rho gasoline. We do have, I guess I should have changed this oil to gasoline. I'll do that on the post slides. Times G times same H, is the same value of H. Because again, these are the same heights. Okay. So we can say that the pressure at K, so that's underneath, so that's the pressure of the fluid just below the piston, is equal to P atmosphere plus the mass of the piston. So I'll use the mass for this, for the K side I'll use the mass of the water piston times G divided by the cross-sectional area. So that's all under pK. So the pK is equal to P atmosphere plus M times G divided by A. And I have this rho water GH quantity. The pressure at N, again, is P atmosphere plus the mass of the gasoline piston, which is what we're looking for, times G. Hopefully not too many subscript letters here. Divided by A plus rho gasoline G times H. Complicated looking equation. So what I first can do is make it a little simpler, cancel out the rho ATMs on both sides, so they would end up cancelling. And I'm going to be left then with these two plus these two. So instead of writing that out in another line, if I were to write this on another line, I could then get rid of the G quantities. So the acceleration due to gravity. So what I'm left with is that I've got MW, mass of the water piston, divided by the cross-sectional area, plus rho of the water, known, plus the height H, known, plus the mass, equals the mass of the gasoline piston, or quantity we want to find, divided by A, plus rho gasoline, or the oil, times H. The only unknown in this equation, linear equation, is the mass of the gasoline piston, which is what we want to find. So I will first, in a sense, bring this across. So the mass of the gasoline piston, think about taking MW over A plus rho water times H minus rho gasoline times H, all multiplied by A. If I just give you the values here, mass of the water is 5 kilos, the area is going to be pi times the radius squared, so 0.02, all to be squared. The rho of the water is given, the H is 0.11 meters, again you can 15 minus 4, so that's the height of those columns. And do I need anything else? No, I don't think so. And this mass works out to be 5.04 kgs. If you call the mass of the gasoline piston, and if you end up plugging in these values. Okay, I've forgotten, just double checking, have everything. Yeah, that's what's good. Yeah, that should be the answer.